So now let's talk about Voronoi graphs, which is another path planning method that we want to look at. Voronoi path planning tries to find paths that are not close to obstacles as opposed to the V-graph, but in fact as far away as possible from obstacles. So you can think of this as a safer path planning method. It creates a maximal safe path in that we never come closer to obstacles than we need to. Let's talk about what a Voronoi diagram is. A Voronoi diagram in the plane is a set of points, pi, called sites. And the Voronoi diagram is a subdivision of the plane into n distinct cells, one for each site. So you see here we've created a set of cells for this Voronoi diagram, and each cell has the property that a point Q corresponds to a site P sub I if and only if the distance from that point to P sub I is less than the distance from that point to any other point in this domain. So you can see all these points that we have as our reference sites, okay, everything in that little area that's shaded on the left, those points are closest to that point and no other point. And so we can see that these sites are defined by these lines which create the boundaries of the sites, and we'll see how we want to use those for our path planner. So if we have 2 points in a site, 2 sites, we can see that the Voronoi graph is simply the perpendicular bisector of those 2 points, okay? And we have 3 points. We have edges that come together into a vertex. So you can see that the edges are equidistant from 2 points and the vertices are equidistant from 3 points. And if you look on the right, we have a 4-point system, and you can see that if you do all the intersections of these perpendicular bisectors, you get a diagram that looks like this, showing you the ability of these points to be oriented towards these cells. So we're really creating a cellular region, and we have these vertices and edges which break those cells up. And if you think of the points as obstacles, you can see that we're going to try to navigate around them via these edges and arcs and vertices of the Voronoi graph. So let me show you an example of this. This is the Columbia campus map on the left, and we have a representation of that on the right. This is the northern part of the campus. And so we use this for path planning with a mobile robot to do laser scanning of buildings on the campus, and we want to automate it so it knows how to find its way around automatically. So given this given this map on the right, we can then create a Voronoi graph, okay, which, as you can see, is a set of these edges and vertices which are equidistant from obstacles as you go through these pathways, and provide safe transit, if you will, through these complicated regions, okay? And so what we want to do to actually create a path is we have to find a start and a goal, and we do a local search to find the nearest point on the Voronoi diagram, which are these green lines, from the start and from the goal, and then connect up to the graph. Once we're on the graph, we can compute the shortest path using A-star search. So you can see here we have a start and a goal position. We get onto the green, which is the Voronoi diagram, and then we can actually then use a graph search to find the shortest path, and again it will be safe. So let's summarize Voronoi graphs. They're difficult to compute in higher dimensions, and 3D obstacles add complexity, so they have a problem with scaling up. The paths can be overly conservative. We don't always have to be far away from obstacles, but these things try to be as far away as they can. It's fragile also. So if you take a small environmental change, like you added a few new sites and a few obstacles, you can significantly change the graph. So dynamic changes are difficult to put into this graph. The next path planner we want to talk about is a potential field path planner. This is a simple idea. You have the robot attract to the goal and repel from the obstacles. So you can think of the robot trying to get to the goal. It wants to get to the goal. It's like a magnetic attraction, but it's being repelled by the forces which happen to be these obstacles. And hopefully you'll reach the goal if you work with these energy forces well. You can think of the robot as a positively charged particle moving towards a negatively charged goal, which is the attractive force. And the obstacles have the same charge as the robot, which is a repelling force. And what we want to do is we want to have states which are far away from the goal, have large potential energies, what we call potential fields. the goal state has zero potential energy once you reach that. So you're trying to do energy minimization as you go through this space, and you start from a high energy position far away from the goal, try to reach a low energy position near the goal. So the path of the robot is a state of high energy to low or zero energy at the goal. You can think of the planning space as an elevated surface, and the robot is a marble rolling downhill towards the goal. So far away, the surface is raised high. Down by the goal, it's very, very low. It's down to zero, and the marble just will roll right down to it. So here's some visualizations. Here's a repulsive force, which is this obstacle with the plus signs. You can think of the robot having a plus sign, also a charge, positive charge, and then you can see the goal is a negative charge. And so we have this kind of trade-off between attractive forces and repulsive forces, which will bend the robot around this obstacle. Clearly the straight line between the start and goal would make it go through the obstacle, but the repulsive force, the obstacle, forces it away, but still attracted toward the goal. This is the overall idea. And we can formalize this a little bit. The attractive energy is the distance to the goal. Okay, so we can say simply find the square distance to the goal, and we can make it zero once you reach the goal. And obviously far away, it's a large distance and it's highly attractive. The repelling energy is simply the inverse of the distance to the obstacles, which goes to zero as we move away. So we get further away from an obstacle, so it's 1 over that distance, and that's pretty much getting close to zero. You can see that as we get very close to the obstacles, the distance on the denominator gets very small, and we get a very high repulsive force. So the potential energy here is the sum of the energy acting on the robot, or the attractive energy, and the repulsive energy. And we have an alpha here, which just weights the relative weight of the two forces, the positive and negatives. Okay, so this tells me what the energy is at every point in my space. And to find a path, we simply move along the gradient of this vector field, which we've created. So the gradient is simply the direction of greatest change. And if we take the negative gradient, it tries to minimize this to go to the lowest value, which in fact is zero, which hopefully will be where the goal is. So this is the idea behind potential field path planning. So here you see a space where we have a start at some point on this grid, which is at 10, 10 in x and y, and we're going to goal 0, 0. And if we use the distance function, x squared plus y squared, square root of that, then you're going to see that you're going to get here this surface. And if you think of a marble starting at the start, it's just going to roll right down to the goal by following the gradient of this distance function, which is, again, the negative gradient will give you the rate of change largest to get back to the minimal state, which in this case is 0. So this is how the attractive forces work, okay? And we can also put in repelling forces, which are the obstacles. So they're high energy barriers which raise the surface in regions of obstacles and then create that repulsive force. And so now the gradient, as we compute at each point, will force you starting to roll downhill from the start to the goal, towards the goal. But as you hit the obstacles, they will put you back into the main area between the obstacles, which is the lowest energy area, and get you around them and then bring you right to the goal. And we use an algorithm called gradient descent for this, which just follows this gradient at each point and takes the lower value of the gradient every time to go to a lower state. And this is how we do minimization to get to the goal. Now there are limitations to this method. Here we have a start and a goal and an obstacle, and we reach what's called a local minimum. So you can see that we're being attracted to the goal when we get inside that horseshoe, but once we get inside the horseshoe, we're being repelled in a sense by the horseshoe itself, that we come closer to it. So the closer we get to it, the higher the energy is, which repels us, which sends us back towards the start. And you reach a point of equilibrium here where you're not going to move at all, and you're going to get trapped in what's called a local minimum. This is another example of that. We have two obstacles, and it looks like there's a nice straight path between them, but you can see that as this robot starts to get into that narrow area between the two obstacles, it's going to be repulsed by these two obstacles, and it can actually be sent back if the energy from the obstacles is strong enough and they're tight enough. then it won't be able to reach the goal. The attractive force can't overcome the repulsive force. So what do you do when this happens? Well, what you can do when the local minimum of attractive force equals repulsive force is take a random walk. And you can see the little black arrow. You can perturb this to say, okay, if I reach a local minimum, and what you need is a memory to remember that you've been there. So once you find yourself back in a state where you're not making progress, so to speak, towards your goal, then you can just randomly choose a new direction and a new amount of distance and perturb where you are to try to break out of this little valley of energy where you are and try to get to the global minimum. So this is a standard method to be used. So let's summarize potential fields. They're more than just a path planner. When you follow the gradient from this energy function, you can provide a simple control function. So you're not only showing the path, but you're showing the robot how to do this. And you can actually relate this to, if you think of the potential as distance, you can think of the derivative of the gradient as the velocity. So it actually gives you a control which you can translate into a velocity for the robot to move. So farther away, the robot will move very fast because you're taking the derivative of a large distance, and as you get closer to the goal, the velocity will slow down because you're very close and you won't have as much of a derivative. And again, this is all due to the gradient descent algorithm. It's also good because it always allows the robot to move from wherever it finds itself. You can think of this more as a continuous method, so wherever you find yourself, there's a control point you know how to move unless you're in a local minimum. Which again is the problem. You can get trapped in local minimum. What's nice is this can be used as an online or local method. So rather than having to know the entire space a priori, which we have in these previous methods, we can actually, as we encounter new obstacles with sensors, we can compute this potential function online. So again, what we're computing is the distance to the obstacles, and even if we don't know where the obstacles are, when we get close to them, we'll pick them up with sensors, and then we can add that to the computation. So for example, you see here a robot with a laser or sonar sensor, and it's getting a 360-degree scan of the distances to its obstacles, and it can use the values of those as input to this potential function for the repelling force. It still has to know where the goal is, that's the attractive force. But you can see how this can be done online, and even if these obstacles are moving, at each time step, you can update this and find the gradient for the best way to go.